morning, my YouTube viewers. It is Crystal here, and I'm here to give you a code review for another Kaggle competition. This Kaggle competition is the Playground competition, Season 4, Episode 5, and what I used is a deep neural network from TensorFlow. I decided that I was going to get back into TensorFlow and learn how to do all things TensorFlow because I had been studying JAX, which is made by the same people that made TensorFlow. And I'd also been studying flags, but there's not enough stuff written in JAX or flags, which made it very difficult for me to work on machine learning projects. And the reason being is because JAX and flags are intended for researchers, and TensorFlow is intended for like regular machine learning operators or machine learning users. And as a result of that, because I had so much difficulty finding JAX and flags code, I decided to go back to TensorFlow and just work on TensorFlow and study all things TensorFlow because it is such a big library and there's so much that you can do just in TensorFlow alone. So I thought, well, maybe I better stick with that. What we used the regression with a flood prediction data set, and the problem statement is to predict the probability of a region flooding based upon various factors. So the first thing that we're going to do is we're going to import all the libraries that we're going to use. So we're going to import TensorFlow libraries later on in the program, but for the purpose of this program, we're going to import NumPy, which creates NumPy arrays and performs numerical computations. We're going to import Pandas, which creates data frames and processes data. We're going to import OS, which goes into the operating system. We're going to import SciPy, which performs scientific computations, such as the Kolmogorov-Smirnov test. We're going to import sklearn, which provides machine learning functionality. We're going to import matplotlib so we can visualize our data. And then we're going to import seaborn to visualize the data statistically. So after we have imported the first part of the libraries, we're going to read the files using OS, and when we have read the files using OS, we get train, test, and sample submission. So we're going to take pandas and we're going to convert those data sets into data frames, being train, test, and sample submission. We're going to set the program up to where you can view all of the columns of data with pd.setOption display.maxColumns none. So you can see train, and train has 22 columns of data, the last column of data being the flood probability, and that's what we have to predict on. We have to predict on the probability of flooding. So we're going to check on train. You can see all of the columns of data or features are numeric. So that's good. So that means that you don't have anything to encode. We're going to check for any null values. There's not any null values. So that's good. So that means you don't have anything to impute. We're going to check test. Test is the same format as train, except for the fact that it does not have a flood probability because that's what we're going to be predicting on. We're going to check for null values in test, and there's no null values, so that's good, nothing to impute. And then we're going to check the submission, and this is what Kaggle wants to see when we submit our data. So now we're going to do a Kolmogorov-Smirnov test. We're going to set our target as the flood probability, and we're going to pop that out of the train data frame. and then we're going to drop the ID column from the train data frame. And the reason why is because you don't need the ID. The reason for that is because Pandas automatically indexes each row of data. So now what we're going to do is we're going to perform the Kolmogorov-Smirnov test to see if any of the columns of data are not from the same columns of data. See if training column are not from the same sample or from the same population. If they're not from the same sample or the same population, then we're going to drop them. So I said if PV is less than 0.1, it can be either 0.05, which is 5%, or 0.1, which is 10%, but I chose 0.1 in this instance. Now, if you want to see if you can get your score better, then what you can do is you can make it 0.05 and see if the error is less. But I chose 0.1 in this instance. And then so you had monsoon intensity is column of data that was not from the same distribution. So I deleted that column of data. Now we're going to remove ID columns because they're not needed. And I've already done that. I should have actually deleted that cell, but I forgot to, but it doesn't matter because we've already done that in the past. Now we're going to analyze target and features. We're going to check the value count of the target so you can see how many instances you have of each number. And then we're going to create a histogram of the target. And so this is the histogram of your target. And we're going to use data sns.histplot, brackets, data equals train, comma, x equals target, comma, KDE equals true. So that's what your target looks like. Now we're going to make a heat map. So core equals train.core, SNS heat map core, and you can see the heat map because most of the boxes are black or close to black. That means that these features have a very low correlation. And since they have a very low correlation, you can't delete them because what you do is when you delete columns that have a high correlation, then there is the possibility that your accuracy could be reduced or your error could be increased. So we're not going to do anything in this instance because the columns of data have such a low correlation. So now we're going to define our x and our y variables. Y is your target, x is your train, x test is test. And then so y is your dependent variable and x test are your independent variables. So we're going to use train test split to split the train and the x and y variables into train and validation sets, and 10% is going to be your validation set. Now we're going to define the model, and we're going to use TensorFlow to define the model. So we're going to import the TensorFlow libraries that we need. So we import TensorFlow as TF, and you see that we're using version 2.15. We set our seed, tf.random.setSeed is 42. And now what we do is we define a sequential model. Flood model equals tf.keras.sequential, layers.dense 64 activation equals ReLU, layers.dense 64 activation equals ReLU, and then layers.dense 1. And then so that is a deep neural network which also performs linear regression. But the thing that you could do, like if you wanted to play around to see if you could improve your score, you could like use a different number other than 64. Like you could use 128 and then 64. So you could play around with a number of neurons to see if you could improve the score. And ReLU is a very good all-around activation function, but you could try another activation function and see if you could improve your score that way as well. So now what we're going to do is we're going to compile the flood model, and we're going to use the loss as mean squared error, and we're going to use Adam as the optimizer. And then we're going to train the model. So we trained the model for 30 epochs, and we did get an error, but we did get an error. All log messages before ABSL initialized log is called are written to STDERRIOOOOOOOO, and then another number. 73 device compiler compiled cluster using XLA. This line is logged at most once for the lifetime of the process. So we got a warning. I'm not sure exactly what that means, but we did get a warning. And then we trained it for 30 epochs. Now, if you want to see if you can improve your score, you could train it for 40 or 50 epochs, and that might actually improve your score. But I just kept it on 30 epochs because it took long enough for me to train it with 30. But if you want to see if you can get a better score, you can try to train it for more epochs. And as far as the optimizer is concerned, Adam is a good all-around optimizer, but you could try a different optimizer such as RMS Prop or Lion or something like that. But I chose to use Adam because it's a good all-around optimizer. So now what we're going to do is we're going to print a summary of the model. So we've got our summary of the model here. And then we plot what the model looks like, so you can check the loss of the model, and you can see that the loss decreases the more epochs that you have, but it does actually settle down to almost a straight line. So I'm not sure that your accuracy or your error is going to decrease if you had more than 30 epochs. Maybe you could try only 15 epochs, but you can experiment with that to see if you can improve your score. So now what we're going to do is we're going to test on the validation set. And so this is what the validation set says. Another thing that I did was I did not normalize the data of the target. And the reason why I didn't do that is because the target was actually a probability, and being a probability, it was going to be between 0 and 1 anyway. So if I normalized the data, then it was not going to make any difference. So I decided not to normalize the data in this instance. So we're going to display our YPRED, which is our prediction. So you can see the YPRED there, and we use SNS Seaborn displot to do that. And our error is 0.02, which is, in my opinion, good. And then we're going to create a data frame with your actual values and your predicted values. And so that tells you how far away the predicted values are from the actual values. And then what I did was I plotted a graph using Matplotlib. And this is what the predicted values are on the dashed black line, and the actual values are the blue dots. And I don't think it looks that bad. Of course, you could get it to look better, but I don't think it looks that bad. So we're going to predict on the test set now. And when we predicted on our test set, this is what the prediction looks like. And we prepare our submission, and this is what our submission looks like. And so basically, when we submitted our work to Kaggle, I got a 79% when I submitted my work to Kaggle. The highest scores were like 86%. And obviously they did more work than I did. So there are things that you can do to try to improve the model, like improve the score. Like you could use a different model, like you could use a model from sklearn, or you could use a different algorithm. But I decided to stick with TensorFlow because I want to learn TensorFlow as well as I can. And then I'm not sure that the accuracy is going to improve if you increase the epochs, but you could try increasing the epochs. You could try changing the learning rate. You could try changing the optimizer there, and you could like not delete that one column of data that I deleted. So you could try to like use all of the columns of data, because one of the things that you have is when you delete a column of data, then what you sacrifice is accuracy. So if you want to try this model and not do the Kolmogorov-Smirnov test and just keep all of the columns of data there, then you may actually improve your score. So that's it for this code review. Hope you liked it. I did actually get a bronze medal on the previous one that I did. The previous one that I did was play 4.5 TF, and this one that I've done today is play 4.5.tfdn. So I did get a bronze medal on the previous one, and the score on the previous one is not as good as the score on this one, which is why I decided to do a code review on this one. So I'm going to go ahead and conclude this video. If you like my video, please like and subscribe. Thank you to my subscribers for supporting my channel, and I will be communicating with you in the next video.